Okay. Good afternoon, everyone. So we were almost halfway through. Okay, not exactly halfway, a bit shorter or a bit before the halfway point of our last chapter, where we had seen some ideas behind multiprocessor systems, the various categories, etc. Right? And we had also seen heterogeneous versus symmetric multiprocessing, and we had seen the advantages of symmetric multiprocessing systems as well as disadvantages versus heterogeneous multiprocessing. Now let us look at an example, a classic example for a heterogeneous multiprocessing system where we are looking at multiple cores or different cores which are having different microarchitectures but same instruction set architecture. So when we talked about heterogeneous multiprocessing, well, we talked about processors, coupling processors or combining processors which are not necessarily identical to each other, right? And when we say not identical, it can mean multiple things. It can mean that their microarchitecture is not identical, but instruction set architecture is identical. It can also mean their instruction set architectures themselves are non-identical. And ARM Big Little is an example for a system where the microarchitectures are different, but instruction set architectures are identical. Okay, it's a heterogeneous, it is still considered heterogeneous because the processors involved are not identical. So it couples relatively battery saving slower processor cores, which are what we call little cores, with relatively more powerful and power hungry cores, which are called big. Okay, and ARM's style of writing is that big is written in small letters and little is written in capital letters. Okay, which they probably thought is cool, which is not bad. Yeah. Okay, so anyway, the idea is to couple different types of processors, but they have the same instruction set architecture. So naturally, you can imagine that those big cores, those power hungry but powerful cores will have a lot more transistors, and those transistors are dedicated to performance rather than power efficiency. Like for example, they are likely to have more pipeline stages, and they are likely to have more advanced branch prediction systems, more forwarding and those kind of performance oriented techniques, as opposed to little cores which are likely to be simpler. Okay, less advanced branch prediction, possibly less number of pipeline stages, possibly introducing more stalls, rather than other better techniques such as forwarding, etc. So that's the idea here. So it's a multi-core processor that aims to adjust your performance dynamically to computing needs. Okay, ARM claims that such a paradigm can help reduce up to 75% of the power consumption that would be there otherwise. There are three main variants. It sort of represents the evolution in big little technology. Initially, when it was introduced for the first time about 10 years ago, it was the first paradigm was what they call clustered switching. It's the simplest implementation where processors are arranged in identical size clusters of big and little cores. So here you see there is a high performance cluster and there is a low performance cluster. Okay, having equal number of cores in each cluster. Earlier examples would be Samsung Galaxy S4, iPhone 7, etc., which used to have clustered switching. So only one of these clusters will be active at any given time. So let's say if you are doing something which requires very low performance, like for example typing a message in WhatsApp, okay, which is computationally quite simple, right? As opposed to playing a game or watching a video, etc., which are naturally more computationally complex operations. So if you are doing some WhatsApp messaging or calling somebody, etc., it will be mostly running on the low cluster. Whereas when the performance requirement becomes more than what the low cluster can really handle, it will switch to the high cluster. And the operating system makes this decision on which cluster is to be utilized. Okay, so that was the preliminary implementation of big little. And then came this rather uncommon second paradigm, which is still within big little, called in-kernel switcher or CPU migration. So in CPU migration, we don't have separate big and little clusters. Each processor comes as a pair. So each processor is logically composed of a high performance core and a low performance core. Only one of them will be operating at a time. So each pair operates as one virtual core, and only one real core is powered up and running at any given time. So you see, there are 4 virtual cores, and for each of them independently you can switch, or it is possible to switch between big and little cores. The operating system need not explicitly know that there are 2 cores available. It can simply make use of DVFS technique. Heard of DVFS? I think I mentioned it in the last class, dynamic voltage and frequency scaling. Modern processors do come with a table which shows all the possible voltages and frequencies that the processor can be set to. And then the operating system, based on the current load, can actually pick up one of the valid entries from DVFS table. So the same technique could actually be used by the operating system to switch between the cores. So certain entries in DVFS, when selected, will cause the higher or the big core to be activated. Certain other entries will cause little core to be activated. And the switching between these cores is sort of transparent to the software. The architectural state gets automatically transferred over. Okay, so from the software perspective, it does look like it's one single core. Okay, whereas in reality, or behind the screens, you have 2 cores. So this is called in-kernel switching. Some of the processors that used to use this technique was NVIDIA Tegra 3 system on chip, which was there in Microsoft Surface. The non-Pro early version used to have this. There was an ARM version of Surface Pro, right? And that used to use in-kernel switching. There are some others like LG Optimus 4X, etc. Now, the third one, which is the one which is used by a significant number of the phones out there, there is a high chance that the phone that you have in your pocket will be using this. This is called global task scheduling. Okay, unlike the early versions, the operating system now has the complete flexibility in deciding which core or which core combinations are to be selected. Of course, there are some terms and conditions involved, but by and large, it was up to the operating system to decide on which core combinations to use. Okay, so it was entirely possible to have, let's say, one so-called big core dealing with a thread which requires a lot of computational load, and the rest of the threads, which are possibly computationally lighter, could be running on the little core or little cores. Now, there is another model now called dynamic, which was introduced I think about 4 years ago by ARM, which is nothing but a superset of ARM Big Little, where some of the original restrictions in the ARM Big Little topology is removed. Okay, you can read up about it if you are interested. It's what is currently the state of the art from ARM. Now, in global task scheduling, threads with high priority and computational intensity are allocated to big cores, while threads with low priority or low computational intensity, such as background tasks, can be performed by little cores. Okay, examples are, well, vast majority of the phones out there do use global task scheduling based big little topology. Okay, now this used to be there only in mobile processors until not so long ago, but a few months back, somewhere in early 2022, Intel has implemented its version of this paradigm in their Alden Lake series processors, where they have golden curve performance cores which are coupled with Grace Mount energy efficient cores. Okay, those which are in brown color are those which I added later, by the way. Now, another example for heterogeneous multiprocessing, but this time it's not big little, or it's more than just big little. It's Apple A4, okay, which is not the latest. You have Apple A16 system on chip, which was released a few months ago, but it is not that radically different from A14, other than better numbers. So Apple A14, which is used in iPhone 12, has 11.8 billion transistors. By the way, A16 has 17 billion, if I'm not wrong. Based on 5 nanometer fabrication process, and even the latest A16 is also still based on 5 nanometer process. But this A14 was the first commercially available device based on 5 nanometer technology. It has two high performance cores called Firestorm. So two big cores which are called Firestorm, and 4 energy efficient cores which they call Ice-Storm. And both these cores run ARM version 8 instruction set architecture. It has a 4-core GPU and a 16-core neural engine capable of performing 11 trillion operations per second. And the neural engine in the newest Apple system on chip allows, I think, about 17 billion. Sorry, 17 trillion, not billion. Yeah, 17 billion is a bit too low. 17 trillion operations per second. It has machine learning matrix multiplication accelerators. Then it has image processor for computational photography. And I think in A16, this image processor is called image signal processor, which is significantly enhanced over A14. It also has a motion coprocessor, which can read all these inertial sensors, environment sensors such as accelerometer, gyroscope, compass, barometer, etc., even when the device is asleep. So even when you have it in your pocket and you are not actively using it, these sensors will be read by the motion coprocessor. And then it will be buffered so that applications can retrieve the data when the device is woken up. So reading all these sensors do not involve your CPU. It is done by a separate processor. Okay, while Apple has not released much details about what the processor is, it is believed to be some variant of ARM Cortex-M series. Okay, which is very similar to the processor that you had used in your CG or EE2028. Okay. So it's radically different from the ARM version 8. So now you see, there are also video encoders, decoders, video codecs to accelerate the encoding and decoding of H.264, H.265, etc. So now you see the system on chip has quite a number of different processors. The newer versions also have some security related hardware or processors as well. So you see there is a lot of heterogeneity. It's not like the CPU is doing all the tasks. No, there are a lot of specialized processors which are all working together to make it very power efficient. If all these tasks were done on the CPU, your battery life will be a lot lower than what you can get by having this level of heterogeneity. Okay, and Apple of course has the advantage that they control both the hardware as well as the software ecosystem. So they can afford to bring out highly tailored solutions, which a lot of other manufacturers are unable to. But having said that, a high level of heterogeneity is there for system on chips even from other manufacturers. Like for example, Qualcomm or Huawei, HiSilicon, etc. All of them have a high degree of heterogeneity. Okay, probably not to the same extent as Apple system on chips, but it's still there. Yeah. Now another slide which I added later. Pairing FPGAs with CPUs is also common for custom hardware acceleration applications. Okay, it's also a paradigm that is getting increasingly popular. And compute using FPGAs is called adaptive or reconfigurable computing. For example, Microsoft Bing search engine uses FPGA-based acceleration. Now, some examples for coupling of CPUs plus FPGAs. You can have the best of both worlds. You have the flexibility offered by CPU. Getting something to run on a CPU is very easy because you just need to write software code, okay, which is a lot easier to write, to debug, etc. But the price that you are paying for that flexibility is that it is inefficient. I think I have mentioned before, CPU is a jack of all trades, but a master of none. It can do everything that you throw at it, but it wouldn't do anything particularly efficiently. So if you want performance, CPU is not the way to go. Yeah. So you have to have custom accelerators which are good for certain type of computations, but only for those kind of computations. You can't really make it to perform general purpose computations. Custom accelerators. Like for example, you have your neural engine here, right? It's not meant to perform, or it's not meant to run your standard type of programs. It's meant to accelerate a certain specific type of applications. So when you go for specialization, you lose flexibility, but you gain efficiency. That's the idea, and that's an inevitable trade-off. You look at almost any engineering problem. That trade-off between flexibility and efficiency is pervasive. Now we have Intel or Altera Cyclone SoC series, which is a combination of FPGA and ARM Cortex-A series processors. Xilinx or AMD also has Sync series, which is again a combination of FPGA plus ARM Cortex series processors. Some of you might have already used it in your modules such as CG3207 Lec, right? Or some of you have taken EE4218. In all those modules, you essentially do custom acceleration using Sync series FPGAs, which is nothing but a combination of a standard multi-core CPU plus a custom accelerator that you create by programming the FPGA. Now, this is an example, or these two are examples where we primarily look at them as FPGAs, but they also have processors embedded within it. Now, the other way around is there too. Examples for cases where you look at them primarily as CPUs with FPGA integrated into them. Some Intel Xeon series FPGAs have, Intel Xeon series CPUs, which are typically used in workstations and servers. Some of them do have integrated FPGAs. AMD is planning to integrate FPGAs into their EPIC processor series, which is also meant for servers and workstations in 2023, that's next year. Okay, now that the AMD has bought over Xilinx, they are planning to have products which integrate the capabilities. And many FPGAs are available as PCI Express cards, just like how it is for GPUs, right? Vast majority of the GPUs use PCIe, X16 interface. X8 if you are looking at a low-end graphics card, X16 or 16-lane PCIe connection if it is a higher-end graphics card. So similarly, there are FPGA cards available which you can buy and plug into your computers. And then you can access them, program them and access them just like how you access GPUs as a custom accelerator. Okay, and I had mentioned towards the end of the last class that OpenCL framework is available from most vendors, and FPGA vendors such as Intel and AMD do have reasonably good OpenCL frameworks to support their FPGAs. So you can actually write OpenCL code, that is a pure C code, to program your FPGA and integrate it with the rest of your system from a software perspective. Examples for such very high performance accelerator cards are Xilinx Alveo series and Versal series. Any guess what is the cost for some of these cards? It's in the range of higher thousands or tens of thousands. Okay, not particularly cheap. Now, FPGA instances are offered by many cloud-based vendors or services such as Amazon. Amazon has this EC2 F1 instances. Alibaba Cloud also offers FPGA instances, and some other cloud providers do as well. Now, that is about it from a multiprocessor systems perspective. Now, let us look at dealing with exceptions. You must be curious, how can exceptions be handled? We have so far looked at a processor which does not have exception handling capability or interrupt handling capability. How do we incorporate interrupt handling capability into a processor from a microarchitecture perspective? Okay, it's simpler than you think it is. We will see that soon. But before that, let's look at exceptions or interrupts in a bit more detail. The two terms are somewhat synonymously and interchangeably used, but it depends more on the manufacturer. Okay, as is the case with a lot of terminology. Some manufacturers, such as Intel, generally tend to use the term interrupts more often than exceptions. There are some other vendors, such as MIPS, use the term exceptions more often. In ARM, both the terms are used. Generally, anything that is generated within the core part of the processor is considered an exception, whereas anything that comes in externally is considered by ARM as an interrupt. So ARM makes a distinction, which can get confusing at times, but there is a distinction at least. So for example, sending an invalid or encountering an invalid instruction or sending a wrong memory address. So all those are considered exceptions. Whereas an interrupt from a sensor, for example, an accelerometer, which has a fault detection interrupt, for example. Then when there is a fault, the accelerometer will give you an interrupt. And that interrupt is considered an external interrupt or simply interrupt. So ARM makes that distinction. But some other manufacturers don't really make that distinction. But that's just a matter of terminology. Whether it's interrupt or exception or whatever, the fundamental idea is that your current program that is executing has to be suspended. And then you go into an interrupt service routine, which will deal with the interrupt, and then you come back, possibly come back and resume what you are doing. That's the idea of interrupts. Now, interrupts or exceptions can arise from arithmetic errors, data processing instructions, like for example a division instruction. When the divisor is 0, can't really proceed, right? Because your result is not okay. And in some architectures such as Intel architecture, divide error is one of the highest priority interrupts. Okay, it's a very serious interrupt. There is really no way the current program can proceed from that point. Trying to execute an undefined instruction, input-output device request, or OS service request. Like for example, you are sending an address and the page table does not have an entry corresponding to that. Okay, that will cause what we call a page fault or TLB miss. So all these are related to memory access or interaction with the OS in a way. It could even be hardware malfunction. Of course, if your processor itself is malfunctioning, it's hard to recover from that. But if it is some external device, then you can possibly recognize that as an interrupt. Now, whether it is an interrupt or exception, the pipeline has to stop executing the offending instruction in midstream. let all the prior instructions complete. So those instructions which are already in the pipeline, which is ahead or in stages which are later stages of execution than the offending instruction, can be allowed to complete. Like for example, you have a division instruction here, but let's say division instruction generates an interrupt when it is in execute stage. But there could be previous instructions which are in M and W stage. And there is nothing stopping those instructions from completing. They are allowed to complete and they should be allowed to complete. But the offending instruction has to be stopped. Flush all the following instructions. So, since this instruction generated an interrupt, the other instructions that had entered the pipeline, for example, those instructions in decode stage or fetch stage, they have to be flushed. Then sometimes set a register to show the cause of exception. Okay, it depends on the specific architecture. In some architectures, you have something called a cause register. And that cause register will have some information related to what exactly caused the interrupt or exception. And save the address of the offending instruction. Because if you need to have a possibility to come back to that instruction, you need to save the address of the instruction. And then jump to a prearranged address, which is the address of your exception handler. And the software or the exception handler, which is in a system with operating system, all exception handlers are considered to be a part of the OS. So the exception handler looks at the cause of the exception and deals with it. And how exactly it deals with it depends on what exactly is the exception, right? Now there are two types of exceptions. There are interrupts and there are exceptions. Interrupts are asynchronous to program execution. What do you mean by asynchronous to program execution? They are generally caused not by a specific instruction that is currently executing. It is something which typically comes from outside. For example, a timer interrupt, or an interrupt from a sensor, or an interrupt from an input device like keyboard. By the way, even output device can generate interrupts, let's say when it wants data. So the previous data that you sent to the output device has already been dealt with, and now it is asking you for more data. So that output device can also generate an interrupt. But these are all asynchronous to program execution. You cannot specifically pinpoint and say, oh, this is the instruction that caused the interrupt to be raised. It's not tied to any specific instruction, right? They are caused by external events, and they may be handled between instructions. So the instructions that are currently active in the pipeline can be allowed to complete. So earlier I had mentioned that if there is a problem with division, we have to stop division instruction and every other instruction after that, right? Whereas if it is an exception, it's not tied to any specific instruction. So there is nothing stopping you from allowing all the instructions that are in the pipeline to complete. Okay, so you can allow the instructions currently running to complete before the control is passed to the interrupt handler. So effectively, the currently running program just gets suspended and later on it resumes. Okay, that suspension is also called in engineering terms preemption. So the currently running program is preempted and the control is passed to the service routine. Once the service routine or the handler exits, the control is passed back to the program that was preempted. Then there are traps or exceptions which are generated synchronous to the program execution. They are caused by internal events or events which are usually directly related to some instruction execution. The condition must be remedied by the trap handler for that instruction. So we must stop the offending instruction midstream in the pipeline, and the control is handled to the trap handler or exception handler. The offending instruction may be retired or simulated by the operating system, and the program may continue or it may be aborted. So it depends. For example, if the exception was caused because of a page fault, what the operating system does is basically fetch new pages from the disk into the memory through a DMA transfer, change the page table entries, and then allow the program to continue. So that possibly load instruction, which had caused the exception to be raised, because load instruction causes a memory access, right? That was probably what caused the exception. So the load instruction can be allowed to continue after the OS does the required stuff. But in some other cases, for example, if the address requested is completely invalid, it's an illegal address. Okay, not because it's not paged, but it's a completely illegal address. Then chances are that the operating system will not give the control back to the program. The program may just be killed. Right? And in Windows, you see this message: this program has encountered a problem and needs to close or needs to be shut down. Sorry for the inconvenience, something of that sort, right? So the OS will typically give a message to the user. Sometimes it may just fail silently, but the OS typically kills the program. Now, this could also happen for example, illegal instructions. So let's say you are running a program which has some instructions which are meant for a newer processor, which is not supported by an older processor. There is a possibility that the programs can still execute in the older processor, but then the OS will have to simulate that particular instruction. Okay, which could happen for some multimedia or vector extensions, etc., which are supported only by newer processors. So if a program is compiled for that processor, the OS can allow it to run on an older processor by simulating that instruction. So basically, whatever that instruction does will be implemented by the OS as a software version. Yeah, as a set of instructions which are supported by the processor. And then once that particular instruction is simulated, the control can actually be handled back to the program that issued that instruction. It doesn't need to be killed. That's the idea. But anyway, the point here is that for exceptions, we have to stop the offending instruction midstream. For interrupts, all instructions that are already in the pipeline can be allowed to complete. There is no need to kill anything. That's the point. Now some stages where exceptions can occur. Arithmetic error typically occurs in execute stage and is synchronous to program execution. Undefined instruction can be caught in decode stage and is also synchronous to program execution. Any memory related issue like a TLB, translation look-aside buffer issue, or page fault, etc., are recognized either in F stage if that happens to instruction memory, or M stage if it is associated with data memory access. And they are also synchronous to program execution. You can pinpoint the specific instruction that caused the issue. Whereas input-output service request can happen in any stage. It is not synchronous to program execution. Same goes for a hardware malfunction or any type of external stuff which is not synchronous to program execution. And beware that multiple exceptions can occur simultaneously in a single clock cycle. So if you are unlucky enough, you could have, for example, data memory page fault, which is recognized in M stage. The next instruction has an arithmetic error, and the next instruction is an undefined instruction, and the next instruction has an instruction memory page fault. So if there are multiple exceptions happening at the same time, the hardware has to sort the exceptions and recognize which one is the earliest instruction that caused the exception. And we also saw some other implications related to this, right? Any other instruction that was already in the pipeline, whether it generates an exception or not, should not be allowed to commit its results. Because if this instruction causes an exception, we have to guarantee, the hardware has to guarantee that the following instructions do not change the machine state. And this might require buffering of various results, flags, etc. And we also saw that in an out of order processor, it's a commit unit that will keep track of which instructions are committed and which is the latest instruction, which is the earliest instruction that actually causes an exception if there are multiple exceptions. So this is the earliest in this case, right? So all these are managed by the commit unit, which will keep track of which are the instructions which are committed, and in fact the order of instructions itself. And that is also why the commit unit has to process instructions in the same order as in the original program. Okay, so that all these issues can be dealt with. Remember, even in an out of order processor, your instruction issue and instruction decoding and instruction commit are both still done in order, even though the execution itself is out of order. So the execution can follow the data order, whereas issue and commit has to follow the program order. Okay. Now let us look at how we can have hardware which can do exception handling. We need a mechanism to load the PC with the address of the exception handler. That's essentially what should happen when there is an exception or interrupt, right? Okay, let's not worry too much about the flushing, etc., etc. Let's look at how an exception can be handled by invoking a handler. A simple way is to expand the PC input mux, where the new input can be either a fixed exception handler address or obtained from a table. So the fundamental idea is just expand the multiplexer that feeds PC. Earlier we had only two possible entries for that multiplexer. One entry was your BTA, the other entry was PC plus 4. And the selection between BTA and PC plus 4 was done using a PC SRC signal, which was a 1-bit signal. Whereas now the PC SRC signal has to be expanded to be a multi-bit signal, because now this multiplexer has more possible inputs. At least one third option, which is the exception handler starting address. And then of course, when an exception is detected, the control unit should assert the PC SRC correctly so that it will be 1-0, that is exception handler address will go into PC, not BTA, not PC plus 4. Now, there are two different approaches to handling exceptions: non-vectored interrupt and vectored interrupt, or exceptions or interrupts. Vectored and non-vectored. In non-vectored interrupt, you always have a fixed exception handler address. So the third input to the multiplexer is a fixed value, a constant value, a hard-coded value. Advantage is that it has simple hardware, because the value is fixed. But more complicated handler software, as it needs to find the cause and deal with it appropriately. Now the interrupt handler is always the same function or same handler, irrespective of which interrupt or exception was raised. And the exception handler software has to figure out what caused the interrupt or exception and deal with it. And in some processes like MIPS, there are registers that record the cause of the exception. Not a very detailed cause, but the rough cause, like for example, invalid instruction or arithmetic and logic unit generating an interrupt. Those kind of things will be recorded in the cause register. So the handler code typically will read the cause register to figure out what is the problem and then deal with it appropriately. So you will typically have a fairly long list of switch case statements. So switch case 1, case 2, case 3, case 4, one case for each exception, right? So that discrimination of what is done is based on what is the cause of the exception, but it is all done in the same function or same handler. And sometimes you may also need to read the various status bits of peripheral registers, etc., to figure out which interrupt or exception was raised. The other approach is called a vectored approach or vectored interrupt, where there is a table which shows the various interrupts and their starting addresses. So there is a table, and the table is typically not so small because in a practical system there could be a large number of interrupts. In some complicated systems there could be hundreds of interrupts. And then for each interrupt there needs to be an entry in the table. So we will have a table. Okay, a table like this, and let's say if for a particular interrupt, say interrupt A, this is an interrupt A handler code in the memory. So this will be the interrupt A code starting address, or interrupt A handler starting address. This starting address will be inserted as a table entry. And assuming that you are using C language for creating these interrupt handlers, which is usually the case, these interrupt handlers are written just like standard functions. And this table now is nothing but an array of function pointers. So you essentially have an array. Each entry in the array or each element in the array is a function pointer. And these entries are typically arranged in such a way that you can use the interrupt or exception number as the index. So you will typically have interrupts or exceptions which are numbered in a system. Exception number 1, exception number 2, exception number 3, and so on. So that exception number will be used as an index. Then whatever the processor finds at that index or that location in the array will essentially be loaded into your program counter. So when an interrupt or exception occurs, the processor needs to have a hardware mechanism to read this table. And this table, like I mentioned earlier, is typically big enough, so it's also a part of the memory. So the processor needs to have the circuitry to issue the appropriate address to the memory, which is typically based on which interrupt was raised. The interrupt number is typically used as an index. And then the memory address is computed, sent to the memory, and the content at that memory location is called your interrupt vector, which is nothing but the starting address of that handler. That is loaded into your program counter through the multiplexer which feeds PC. Of course, you can imagine that now the hardware is more complicated. But the advantage is the software is typically simpler because there are different functions that deal with different interrupts. So if a particular function is invoked, the function doesn't have to really check why it was invoked. For example, if there is a handler to deal with keyboard. So when you press something on the keyboard, assuming that the keyboard is configured to generate an interrupt, you will get an interrupt, and the interrupt service routine doesn't need to check why it was raised in the first place, because the handler is associated with keyboard. So it's a key press or something related to keyboard that caused the handler to be invoked. That's the idea. So the software does not have to do any kind of searching to identify what was the interrupt. By the way, having said that, many hardware peripherals are complicated enough that they can generate interrupt in various different circumstances. Like for example, if the interrupt comes from an accelerometer, a typical accelerometer you can buy from the market can generate interrupt in a lot of different scenarios, depending on how it is configured and what all scenarios are enabled to generate interrupts. Like for example, there could be tilt detection, fall detection, threshold based interrupts, motion detection based interrupts. So, once you get an interrupt from accelerometer, there will be one function which deals with that. That will be automatically invoked. But inside the function, you have to identify the exact cause. You know it's from accelerometer, but you don't know what situation in accelerometer caused that interrupt. That may require further identification, which typically requires the handler code to read certain registers within accelerometer to figure out what really caused the interrupt. Okay, so it doesn't mean you can identify the exact cause, but you can more or less identify which device caused the interrupt, at least. And that's already a lot easier as compared to the previous approach where you don't even know which device caused the interrupt. You have to do further processing to figure out which device caused the interrupt. And that makes your software more complicated and possibly less responsive as compared to this. Because the software code might need to execute or check a lot of different things before you identify the exact cause. Whereas here the cause is identified in a lot more straightforward manner. That's the idea, or that's the advantage of vector interrupt. But from a hardware perspective, it's certainly more complicated. Okay, now for exception handling, we need to flush offending instruction and the ones that follows it in case of exceptions. For interrupts, we don't need to assert flush. Some processors automatically save some registers onto the stack. Now, why do we need to save registers? Let's say your main program was executing. At this point, it got interrupted or preempted due to an interrupt or exception. Let's assume that it's an interrupt, okay, which is definitely easier to deal with. So let's assume that an interrupt was raised at this point. Now the control is handed back to handed to your interrupt service routine for that interrupt. Your interrupt service routine runs until completion, and then you go back and continue the main program. But there is a small problem. The interrupt service routine itself is running on the same processor. It may make use of the same registers that were used by the main program. But the main program functionality should not be affected because of the interruption. So we need to ensure that the current state of the main program, which typically involves saving all the registers, general purpose registers as well as some special purpose registers, they should be typically saved somewhere. And the typical place that it will be saved to is your stack. And then you go to your service routine. Once the service routine is finished, everything that was pushed to the stack has to be popped back from the stack. And then your main program continues. Now those who have taken EE2028 might find many of these familiar because interrupts were covered in a great detail in that module. Now some processors automatically save some registers onto the stack. Like for example, ARM Cortex M3 or M4, they push your program status register, program counter, R0 to R3, R12 and link register to the stack automatically. So whenever there is an interrupt, all these will be saved automatically. Now, in the case of other other registers, like I did not include all the registers here, right? There are registers R4 to R11. R4 to R11, if need be, should be saved by the handler itself. The hardware will not do it automatically. It has to be saved by the handler. You might remember that you had written assembly language functions in your CG or EE2028, right? You had pushed some registers onto the stack at the beginning of the function and popped them at the end. This is so that those registers will not have their contents altered by your program or your function. So if you recall, you have to actually push only R4 to R11, not other, and R14 if need be, by the way. But other registers need not be really saved. Why is it so? Because R0 to R3, R12, etc. are what we call caller saved registers. So the caller, so for example, if it is a standard function that is called from a main program, the main program will ensure that there is nothing in R0 to R3 and R12 that should be kept unchanged by the function. But these registers are what we call callee saved. So it is a responsibility of the callee function. That is a function that is getting called to save these registers. Now you can draw parallels with what you see here. Here, interrupt service routine is written like a standard C function. Just that it is not called from the main program. It's not a function that is called by another function. It can be thought of as a function that is called by the hardware. But C compiler doesn't know whether it's an interrupt service routine or a standard function. The compilation process is done exactly the same way. So if the function uses these registers, they should be pushed to the stack and poked from the stack before exiting the function. Same goes for interrupt service routine. Okay, so all the registers that the main program would have saved if it was a standard function call should now be saved automatically by the hardware. Because now the hardware is calling the interrupt service routine. Got the idea? And that's why all caller saved registers should also be saved by the hardware. Whereas callee saved ones are left to the handler, which is written like a standard function. Now, I just mentioned that the compiler doesn't know whether it's an interrupt service routine or a standard function, right? Then how will the hardware know that it is supposed to be invoked? Well, you have to create a table like the table that I had mentioned earlier here. This table will have function pointers as entries, right? So the specific interrupt service routine will be nothing but a function pointer in the table. So the processor will look at the table, load the function pointer value into program counter. So that will be essentially a function call made by the hardware. So the compiler doesn't need to know, and the compiler doesn't know that it is a standard C function, or whether it's a standard C function or interrupt service routine. It's compiled the exact same way. Now, you typically need to save the return address to a register like link register. So the link register will be overwritten with the return address, just like how it is for a function call. But any existing content of the link register should also be not overwritten, right? Not lost. And that's why link register is also automatically saved by the hardware. Link register is also callee saved, not caller saved. So the callee function, which is an interrupt service routine, give me a moment. Link register is a bit special because it's normally a callee saved function, callee saved register, but since your interrupt service routine is invoked by the hardware and the return address is overwritten or written into the link register, whatever is in the link register still has to be saved. Okay, so the hardware will save it even though it is actually normally a callee saved register. Now, all this caller saved, callee saved, etc. are based on something called, it's under the umbrella of, we saw that term earlier. ABI, or to be specific, calling convention. Calling convention specifies who saves which register. So calling convention is one of the important aspects of ABI. So according to ARM ABI, R0 to R3 are used for passing parameters. So the caller function will not save anything that should not be destroyed. So they are what we call caller saved function, caller saved registers. Okay, whereas R4 to R11 are not used for passing parameters. So it is a callee whose responsibility or who is responsible for saving the values. So everything caller saved plus link register will be saved automatically by the hardware. Now R13, which is a stack pointer, was not mentioned here. Any guess why? R13 doesn't need to be saved. Interestingly, in ARM Cortex M3, M4, etc., there are two copies of R13. The R13 that is visible to your main program is not the R13 that is visible to your interrupt service routine. Okay, such registers are what we call banked registers. That's what is mentioned here. In some processors, there are separate copies of some registers for use by the handler, which reduces the amount of data to be saved and restored. So in this case, since R13 is a banked register, you don't have to save and restore R13. Now, interrupt processing can be complicated if there are many interrupt sources. So in a practical system, especially in an embedded system, in an IoT system, etc., there could be a large number of devices, sensors, etc., which can generate interrupts. So many systems include an interrupt controller, which is a separate unit that is closely coupled with the processor that contains control registers for enabling or disabling interrupts, setting priority of interrupts, etc. So again, those who have taken EE2028 might find this term NVIC familiar. Nested Vectored Interrupt Controller, which is an interrupt controller that is used in ARM Cortex N series processors, which is like the manager of the interrupts in the system. Okay, imagine that you are a busy CEO of a company. You wouldn't be dealing with every appointment request yourself, right? You will typically have a manager or a secretary who will work very closely with you, and he or she will be the one managing all the appointments for you. And similarly, in a system with a large number of interrupts, the processor does not really deal with interrupts separately. All the interrupts typically go to an interrupt controller, and it's an interrupt controller which will decide whether a particular interrupt should be passed to the processor or not. What is the priority of that particular interrupt if there are multiple interrupts occurring at the same time, etc. But the interrupt controller does not take all these decisions based on its own preferences or whims or fancies. How will it make all these decisions on which one is to be allowed if multiple interrupts happen at the same time, which should have a higher priority, etc.? They are typically eventually decided by the processor, but the processor gives all that information by writing to the various registers within the interrupt controller. So your interrupt controller will have enable registers, priority registers, etc. to enable a particular interrupt, to set the priority of a particular interrupt, etc. And then later on, when an interrupt comes in, the interrupt controller will check what is its priority, whether it is enabled, etc., and decide how to deal with that interrupt, whether it should be passed to the processor or not. Now, that is from a hardware perspective. How do you write an interrupt handler, or what does the handler do? It will save additional registers if needed. Let's say if your interrupt handler makes use of only R0 to R3 and nothing else, then the handler need not save anything, because R0 to R3 is automatically saved by the hardware. You don't have to save it. But if you are using a register which is R4 to R11, which are what we call wholly saved registers. Then since the interrupt handler is a wholly function, you have to save it. Okay? It's just that it is called by the hardware, but it is still considered a wholly function. So any register that is used by the handler in this range has to be saved. Then check which peripheral or condition within the peripheral caused the interrupt. So there could be multiple peripherals which generate the same interrupt. Sometimes you could have two devices whose interrupt pins are all together and go as one single interrupt to the processor or the interrupt controller. In which case, once you get the interrupt, you still need to further identify which of the two possible devices actually raise the interrupt. And sometimes one peripheral can generate interrupt for multiple conditions. Remember the example of accelerometer that I gave? There could be multiple different situations where the accelerometer can generate the interrupt. And then you need to identify the exact cause. Yeah, so inside the handler for this particular interrupt, you have to read the status registers to identify which peripheral it is and the exact condition within the peripheral that caused the interrupt to be raised. And third thing that you do is, now that you identified what is the cause of the interrupt, you had also saved everything that you wanted to save. Now you just need to deal with the situation. For example, if the interrupt came from a keyboard, and you identified that the keyboard raised the interrupt because it has some new data to give you, and that typically happens when the user has typed or pressed a key on the keyboard. The logical course of action would be to read the key that was pressed by the user, the scan code or whatever, and store it into some buffer. And then it should be subjected to further processing, right? But the key point to note is, when you write an interrupt service routine, don't do further processing inside the service routine. Do the bare minimum required to deal with the interrupt. The example that I typically use is that the mindset of a person who is writing an interrupt service routine should be the mindset of a person who is entering a burning building to rescue somebody. What will you do if you enter a burning building? You pull the person out and get the hell out of the place as soon as possible. You will not go inside the burning building and ask the person, do you know why the fire got started? You will do all investigations later on, right? Not inside. So same thing inside your service routine. You do the bare minimum that is required and come out. Don't do any high intense or computationally intensive data processing. Like sometimes when you press something on the keyboard, you read the when the user presses something on the keyboard, you read the keyboard, and the value that is read might require further processing, right? Like for example, spell checking or saving into a file or whatever. But all those will be done outside your handler, not inside your handler. Inside the handler, do the bare minimum. Grab the data and possibly set a flag saying that, oh, there is a new data available. And any further processing which is typically required will be done not inside the handler, but by a part of your code which is having a lower priority than your handler, which is typically your main program. Okay, so do the bare minimum, and that typically involves invoking some codes which will run at a lower privilege level and a lower priority to do further processing. This is typically some kind of a worker thread that is woken up by the service routine. So the interrupt service routine will wake up a thread which was sleeping and waiting for data. So you wake up that thread and then exit the handler. And when the time is right, the operating system scheduler will cause that particular worker thread to run and deal with the rest of the stuff. or do the further data processing. So sometimes we call it the top half and the bottom half of the handler. The top half is the real interrupt handler. The bottom half is typically a user level thread which deals with the data that is available. And then clear the interrupt. So do the bare minimum required, set a flag or whatever if need be, and then clear the interrupt, which is telling the interrupting peripheral to deassert the interrupt request. So if one person raises an interrupt, like you raising your hand if you have a doubt, I will ask you what is your doubt, and once you realize that your doubt is being dealt with, you will lower your hand, right? And sometimes I may have to explicitly tell you, now that, well, I am clearing your doubt or I am dealing with your question, could you please lower your hand? And that process is clearing the interrupt. If you don't do that, the interrupting device could keep the interrupt request asserted, which can end up being treated as a fresh request. But there is nothing standard about the way the interrupt is cleared. That depends on the specific peripheral and also the condition within the peripheral that was the interrupt. To do further processing, set a Boolean flag for the main program or wake up a thread, which is what I just mentioned, the bottom half of the handler. Then restore additional status or registers if any. So anything that was saved here should be restored here. And then you exit the handler. So this is what you do in software. And exiting handler will typically involve restoring the original PC value so that you can go back to the point in code which was interrupted. Okay, now modern processes do have multiple modes. Sometimes they are also called rings. There are different modes or different levels of privilege. Fundamentally, they are of two different types, even though many modern processes do have more fine-grained levels. But fundamentally, they are two, thread mode and handler mode. Thread mode is a mode in which application software, user-level software is executed. The processor enters thread mode when it comes out of reset. It can be privileged or unprivileged. So thread mode itself can be privileged mode or unprivileged mode. Then there is handler mode, which is used to handle exceptions or interrupts. And once the handler quits, the processor returns to thread mode and the thread mode will continue. And handler mode is always privileged. Now what exactly is privileged versus non-privileged? Oh, by the way, I did mention user level here. Okay, that's probably not the right word to use. Basically, executing normal software. Will be clearer once I look at unprivileged versus privileged mode. So thread mode can be of two different types, privileged mode or unprivileged mode. In unprivileged mode, which is called the user mode, so I incorrectly used the term user here, I shouldn't have. Yeah? User mode is only one part of the thread mode. It's unprivileged mode where the software has limited access to certain instructions and cannot use certain instructions. So for example, in ARM Cortex M4, there is this instruction called CPS. Okay, it's not your standard instruction which is used for data processing or memory or branch. CPS is a special instruction called change processor state. It cannot be used in unprivileged mode. So unprivileged mode cannot change the state of the processor. Cannot change the mode of the processor. It cannot access system timer, interrupt controller, or system control registers. So a lot of functionality that is very critical to the system is not accessible in unprivileged mode. And it also might have restricted access to memory or peripherals. So as you can imagine, a program which is run at the user level, which does not have the kind of privileges that are typically available to an operating system, that runs in unprivileged mode or user mode. Whereas privileged mode or supervisor mode is a mode in which the software can use all instructions and has access to all resources. Only privileged software can change the privilege level for software execution in thread mode by writing to control register. So certain instructions and changing privilege levels or modes etc. are possible only in privileged mode. Yes. So the operating system typically runs, or operating system kernel typically runs in privileged mode. So it's only the operating system kernel that has access to all the resources, like for example system timer, interrupt controller, etc. Okay, whereas unprivileged software cannot tamper with some of these systems. Now, why do we need to have this kind of a privilege level? In simple terms, this is basically also called kernel mode. It's a mode in which OS kernel runs. This is the mode in which application software runs. So if application software is allowed to change the mode or change the interrupt settings or stop the timer, etc., it can prevent the operating system from gaining control again. And remember, we had mentioned in the last class or seen in the last class that operating systems, modern operating systems make use of timer interrupts to gain back control if a particular thread does not give up control voluntarily. That's what we call preemptive scheduling or multitasking. So in order to gain back control, timer interrupt should work. So the user software, unprivileged software, should not be allowed to mess with the system timer or change the interrupt settings, etc. So basically a lot of critical operations can be performed only in privileged mode, not in user mode or unprivileged mode. So unprivileged software can use supervisor call instruction in ARM to make a supervisor call to transfer control to the privileged software. So if let's say a user level thread needs some attention from the operating system, like for example to get more memory or to read from an input-output device, etc. These cannot be done directly by user code. So the user code will invoke the operating system, will get service from the operating system by executing SVC instruction, supervisor call. And supervisor call instruction will cause an exception. And that exception handler is a part of the operating system. And handlers always execute in privilege mode. So now you have a switch from user mode to privilege mode. But that is possible only through a supervisor call or a similar exception, or because of a timer generating an interrupt or exception, or because of the application program entering into some kind of an error situation, which could also cause exception. So all these scenarios cause the control to be handled to a handler, which is privileged. And the handler is a part of the operating system, so the OS gets control. Got the idea? So now you can see that unprivileged instructions or unprivileged mode is unable to make changes which are critical to the integrity of the system. And any attempt to make use of some resources that are not supposed to be used will cause an exception. And the exception handler is a part of your OS and runs in privilege mode. Okay, so these are all protection mechanisms that are incorporated into modern processors to facilitate the OS being in control of what's going on. Got the idea? So thread mode can be privileged or unprivileged. When the system starts up, it will be in threat mode and it will be in privileged mode. And the privileged software will hand control back to unprivileged software by setting an appropriate control register. Okay, to switch the mode to unprivileged mode. And then the unprivileged user level code runs. And when it times out, or when it generates an exception, or when it requests for a service, it will cause an interrupt or exception, and the exception handler is privileged software. So it gains back control. Okay, and modern Intel processors do have more than this many modes. There are a lot of different modes with different privilege levels. Okay, but fundamentally, two types of privileges, unprivileged and privileged, and two types of mode, threat mode and handler mode, where threat mode can have both privileged and unprivileged. Handler mode is always privileged. This is the case for ARM Cortex M4, by the way. So I've got some idea of how processor design or processor designers need to be aware of how the operating system interacts with the processor and how the operating system integrity can be ensured, how the user level program can be prevented from doing something malicious, etc. Right? So that's all based on these kind of privileges and protection. By the way, having said that, modern operating systems do not run entirely in privileged mode. There are still parts of the operating system that are unprivileged. And depending on that, there are various types of kernels, OS kernels, such as you might have heard of this thing called monolithic kernel, hybrid kernel, etc. Linux uses a monolithic kernel where almost the entire kernel runs in kernel mode or privileged mode. Whereas in Windows, the kernel doesn't always run in kernel mode. Some of it runs in unprivileged mode, or a good part of the operating system runs as unprivileged. Only some part of the operating system is privileged. That's called hybrid kernel. Now that's about it for interrupt handling. Now let us look at input output. But probably before we look at input output, we can take a break. Again, some of these concepts were already covered in EE2028, but not everyone has taken that module, so it's reproduced here. Okay, welcome back. Okay, so now let us look at some input-output concepts. Now before that, let's look at how a generic computer system will look like. Because since computers come in a lot of different forms and shapes, the exact structure of a computer will vary depending on the exact system in which it is being used, right? But every processor has a CPU or CPUs. Then we have flash memory or some kind of a non-volatile storage. Then RAM, where the data is temporarily stored. Flash memory is non-volatile. RAM is volatile. Non-volatile and volatile. And this is the processing element. These are the storage elements. This is a temporary storage. This is a permanent storage. But that alone is only a part of the story. It's like a brain without a body. So there are these body parts, which are, for example, interrupt controller, which is the manager of interrupts in the system. You have system timer, which is a timekeeper of the system. And then we have those peripherals which allow us to talk to the external world. Those so-called controllers, such as you have your USB controller, you have your Ethernet controller, HDMI controller, I2C controller, etc., etc. And USB, as you can imagine, is connected to a USB-based device like a keyboard or mouse, Ethernet to another computer, HDMI to a display, and interfaces such as I2C for interfacing relatively low speed sensors such as accelerometers, gyroscopes, etc. And historically, all these were separate chips which were soldered onto a motherboard. But increasingly, many of these are getting integrated into one single chip, which is a system on chip. Now, even though all these are interconnected logically using a bus, in reality, it's a network of buses. It's not one single bus which connects everything. Some of the peripherals here are relatively low speed peripherals. For example, I2C is a very low speed peripheral. The typical speed that we are looking at is, for example, 100 kilobits per second. Whereas many other peripherals such as Ethernet, HDMI are much higher speed peripherals. So they talk to the processor at a much faster rate. So what we typically have is a multi-tiered bus system. We have high-speed buses and low-speed buses. If you recall what the Gus lecturer told you a couple of weeks ago, ARM has all these advanced high-speed bus, which are high-speed buses, and advanced peripheral bus, which is a low-speed bus. Think of it as an expressway, and this as a normal road or a country road. And to go from expressway to country road or vice versa, you will have exits, right? Expressway exits. So similarly, we have bridges. A bridge is a hardware device which connects two separate bus systems. So here it is a high-speed to low-speed bridge. And high-speed buses typically are used to connect very high-speed peripherals such as, or very high-speed devices such as RAM, graphics cards possibly, etc., etc. And they are more often than not proprietary. For example, you have your Intel Quick Path Interconnect, AMD Hyper Transport, AHB from ARM, etc. But AHB is actually an open standard. The other two are proprietary. Yeah.
It's high-speed bus like a module of its own that is in charge of it, and there's its own clock, and it's in charge of transferring data.
Yeah, you could say that. It of course has some associated circuitry like some level of address decoding, access control mechanisms, etc. And there is a bus protocol as well, like some set of standards that devices involved have to follow so that they can send data over.
So if I design a processor, can I just use existing buses then?
Yes, in fact, it's quite popular to use existing buses even if you design your own processor. Okay, like for example, AHB is a very good choice if you want your own processor to be designed, because AHB is an open standard. You can just use it even though it was devised or designed by ARM. There are some other bus systems such as Quick Path Interconnect, Hyper Transport, etc. are proprietary. Even the details are not available fully in public domain, and you can't use it without paying royalty. And even if you pay royalty, Intel and AMD probably won't allow you. Okay, whereas AHB is open standard, so you can use. For low-speed buses, again there are various standards, APB or variants of APB like AXI. They are typically industry standard. PCI Express, relatively lower speed bus. They may or may not be proprietary. Like some of these are designed by interest groups, which are companies coming together to agree on a certain standard. Which doesn't mean it's an open standard, you can use it any way you like. You might still have to pay royalty for the intellectual property involved. Okay? Industry standard does not mean open standard that anyone can use. No, you can. It's a set of standards that are publicized by ARM. So as long as you follow those set of standards, various IPs that follow the same standard can talk to each other. Okay, and historically, high-speed buses used to be a part of a chipset which was called North Bridge. And low-speed buses were a part of South Bridge. But these days, North Bridge is integrated into the processor itself. South Bridge can still be separate. May or may not be separate depending on the capabilities of the processor. But historically, it used to be two separate chips on the motherboard. So if you have a motherboard lying around from maybe 15 years ago, you can see there is a slot for a processor. There is one very big chip with typically a heatsink attached, which is the North Bridge. There is another smaller but bigger than all other chips, which typically does not have a heatsink. Sometimes it has, which is your South Bridge. And South Bridge and North Bridge together were known as chipset. But now the trend is to integrate many of these into the processor die itself. Or sometimes it's a separate die but within the same package, which is the case for AMD Ryzen Threadripper series. It's a separate die but in the same interface. Sorry, same package. Now, the software, the driver software, interacts with hardware by reading or writing various registers within the hardware. So, for example, to talk to the USB controller, the processor will write or read registers within the USB controller. Peripheral registers are accessed more or less like memory. There are specific addresses for peripheral registers, and by issuing those addresses, you are accessing the specific registers. They are typically accessed using LDR STR if you are looking at an ARM-based system. But if you are writing it in C language, you don't write LDR STR directly. Instead of that, you will use pointers. So if you write something like, say, A is equal to some star B, you are in some sense using an LDR instruction. Okay, so this is typically done to read a register where B corresponds to the address of the register. Or you could do something like, say, B is equal to, or star B is equal to A. Then you are essentially doing an STR. We are writing to a register. So this is a read and this is a write. Okay, but in C language, we will make use of pointers. At an assembly level, you will do LDR STR. That's the idea. Now there are three categories of registers. So registers can be classified as three different types. Status registers, which are typically read-only registers. So you read status registers to know the situation of the peripheral or the situation of a transfer, etc. So for example, if this peripheral is supposed to talk to another computer or another sensor, for example, if the sensor gave you a data, the data could be stored in some register here, but some new data available flag within a status register will be set automatically by the hardware. So once a new data is available, new data available flag will be set by the hardware. So the software, which is typically the driver program, will read this particular bit within the register. Read the register, extract out the bit, and see whether it is 1 or 0 to figure out whether a new data is available or not. So those are status registers. I mean, what I gave is just an example. It could be related to a data being available, it could be a data required to be written by the processor, it could be related to some error conditions, etc., etc. But these are all status information which are written by the hardware and read by the software. So status registers are typically read-only registers. Then we have control registers, which are meant to be written by the hardware, written by the software to give control information or settings to the hardware. So software writes to these registers to control the hardware. For example, to set the speed at which the data is transmitted, or to set the size of the data to be transmitted, etc., etc. These are control information which are written to control registers. So control registers are, well, conceptually write-only registers, but you very rarely have write-only registers. They are typically read-write registers, even though they are primarily meant to be written. You write to those registers to control the hardware. That's the idea. But why do we want to read it? To just read back what you wrote. So if you don't know what was the control information that you wrote earlier, you may want to read it back. And this is typically done when you want to change only some parts or some bits within the control register. You read those bits or the entire register, modify the required bits and write back. So let's say if this is a control register, I want to modify only one bit within the control register. We typically read it, then modify the bit to the appropriate value, and then you write back. So that requires the register to be read-write registers, right? Though primarily the action that you perform is writing. Then we have data registers, which are meant to be read to get the data and written to give the data. So for example, if this hardware is meant for communication with another device. So if you want to send some information to this particular device, you will write to a register within the peripheral, and then the peripheral hardware will send it over to that device. And if you get some information from the device, it will be captured into a register, and the software will read from that register to get this information. Okay, so they can be read or written. Read for input, written for output, to perform actual data transfer. Now, typically, all the register-based or register-related information is found in the specification sheet or data sheet of that particular device or peripheral. So, for example, if you are using a certain USB controller, there will be some documentation for that USB controller which specifies which are the registers to be read to get some status, to be written to control something, or to be read or written to exchange data, etc. So all that information will be there in some documentation somewhere. And for discrete devices that you buy from market, that information will be available as a data sheet. But having said that, not that you might not have access to a data sheet of a device just because you bought that device. Some devices might require you to sign a non-disclosure agreement before the manufacturer will give you all this information. Okay, whereas for some others, the data sheet might be publicly available. Okay, so don't take for granted that just because you bought a device, you will get information or all the information related to that device. Not necessarily. So typically, the job of reading or writing these registers are encapsulated as driver functions or into driver functions. So you typically have driver functions which encapsulate this. And these driver functions may be available as source code, or in some cases it may be available only in the binary form. Okay, which is typically the case for a lot of hardware. You get only binary versions of drivers. So the exact process of reading or writing these registers is not visible to you. All you can do is to call the binary function, the compile function that is already available from your program. So this software that encapsulates this process of reading or writing these peripheral registers are what we call driver functions. And a collection of driver functions is what we call a library. They internally make use of pointers to various peripheral registers to accomplish this reading or writing. And having libraries allow ease of programming, so you can deal with or you can read from a device or write to a device at a higher level of abstraction. So as a user or as an application programmer, you need not reinvent the wheel. And like I just mentioned, it may not always be the convenience of the application programmer. Sometimes these drivers are available or made available in binary form, compiled form, just so that you will not be able to reverse engineer things. You will not be able to get much insights into how the hardware works, which is hard, but companies need to protect their intellectual property so that you don't copy it that easily. Okay, sometimes these pre-compiled versions of codes which are used to deal with a particular peripheral is sometimes called a blob, B-L-O-B. So sometimes drivers are available only as blobs, not as source code. Now sometimes people end up reverse engineering and figuring out all this stuff, which is not entirely illegal. It depends on how you look at the law associated with all these. So a lot of drivers which were originally released as blobs are actually available as open source now. Okay, one fantastic example for such a driver is AMD graphics card drivers. Okay, there are open source versions which were implemented through reverse engineering, and the open source version is actually even better than the proprietary one in many cases. Okay, it also allows portability. So let's say you are changing the device. Let's say you are using an accelerometer. Now a new version of the accelerometer is available. In order to use that new accelerometer, you don't have to do a complete re-engineering. You just need to change the driver. And the driver interface or API might be exactly the same. In which case, your main program need not even be recompiled. You just need to relink your main program with the new library. Okay, so that's how interfacing with hardware works in real life. Now let us look at some technicalities on how the processor can access an input-output device or register. I had mentioned that it is using LDR-STR instructions, right? But that was a bit of a simplification. That's not the only way. There is an alternative technique called port-mapped input-output or PMIO, where there are dedicated instructions for input-output. Classic example for a processor which supports PMIO is Intel processor or x86 processors, where there are dedicated instructions for input-output. So memory access and input-output access are done using separate instructions. So for example, in Intel there are in-out instructions, in for input, out for output, which are meant for input-output access, not for memory access. The processor has an output pin that specifies whether the address is meant for a memory or a peripheral. So here in the diagram, I have shown a separate memory bus and a separate input-output bus. So logically, they are separate buses. So it's entirely possible to have one particular address, let's say 00101010. So this particular address can be there in the memory, but the exact same address can be there in an input-output device. So an IO register can have the exact same address too. Won't it cause an address clash? Not really, because they are separate address spaces. They do not logically overlap. You can think of it as a totally separate connection going into input-output and memory. So when you are intending to do a memory access, you will do a memory instruction like LDR-STR, and then the data will be sent through memory bus. Whereas if your intention is to do input-output, then the data will be sent through I/O bus. So there is no confusion regarding which device it belongs to, or whether it belongs to memory or input-output, because they are separate. They reside in separate address spaces. Advantage for this is that you have separate address spaces, which means memory can use the full range of addresses. So in a 32-bit system, theoretically you can have 4 GB of memory. The entire range possible, like for example 0000, 0000 to FFFF, can be used entirely for memory. Whereas in the other scheme that I just mentioned about earlier, where we use LDR STR for memory as well as input output, you cannot have the same address for memory and input output. So if you are issuing a particular address, it belongs to either memory or input output, not both. And that also naturally means that in a 32-bit system, you cannot have a full 4 GB memory, because some memory addresses or some addresses have to be reserved for input output, which cannot be used for memory. So you cannot install, for example, a 4 GB RAM in a system that uses memory mapped input output for 32-bit. For 64-bit, that is not really a concern, because the 64-bit address space is quite huge. So not a problem really. Another advantage of port mapped input output is simpler software. The software that performs input output is actually simpler than that of the other technique. The other technique is called memory mapped input output, by the way, because input output and memory follows the same set of instructions, whereas here you have dedicated instructions. So the software is actually simpler, but it is not compliant with RISC philosophy, and you require extra pins. Because at a hardware level, at the level where things come out of the processor, you already make a distinction between memory and input output, which will end up requiring more pins from the processor. Okay, and having more instructions goes against the RISC philosophy of keeping things simple and stupid, right? So let's look at the other technique, alternative technique, port mapped input output, which is essentially what you might have used so far whenever you dealt with input output, especially in ARM-based systems. Address space is shared between memory and input output, and there is an address decoder that determines whether you are issuing the address corresponding to a memory or an input output device. So the address is sent through the same bus. Memory and input output are logically connected to the same bus. So by looking at the address, an address decoder, typically there is an address decoder which will enable either memory or input output depending on the address range. If the address issued is in the address range corresponding to memory, then memory will be activated, otherwise input output. That's the idea. So processor design is simpler because processor does not discriminate between memory and input output. So the number of instructions that the processor needs to implement is now less. But the maximum possible memory is reduced, which I just mentioned, which is not a problem for 64-bit systems, but can be quite a limiting factor for 32-bit systems. Okay, and that's why in the era of 32-bit computing, which was about 10-12 years ago, or I would say 12-13 years ago, we couldn't have a full 4 GB memory in many computer systems. Even if you install 4 GB, you will be able to use only 3 point something GB. That was because some addresses were taken up for memory mapped input output. And while the hardware design is simpler, processor design is simpler, the software now becomes more complicated for memory mapped input output. And that is generally the case for RISC. RISC software is usually more complicated than CISC software, because a lot of complexity is now pushed to the software because the hardware is simpler. And here the software is more complicated, and that complexity comes in a number of different forms. One complexity is related to cache memory. In port mapped input output, cache memory is connected only to the memory bus, not to the input output bus. So the requirement of not having a cache for input output was met automatically and quite easily. But here that's not the case. So the bus that goes out of the processor, the memory or input output bus, has a cache here. Okay, the cache controller is the one which actually talks to the actual bus, not the processor directly. So every address issued by the processor first goes to the cache, and only if the cache controller forwards it, it appears on the real bus. So there is this middleman, and that causes a problem, especially or specifically for input output. What is the problem? Let's say this input output that you are talking about is a keyboard that has a specific address. So one time you read the keyboard, the data from keyboard is now stored in the cache. The next time when you try to read the keyboard, you will end up reading the exact same thing. And that's not good, right? The user must have trusted a new key. So you should be reading the new data, but if the data is cached, you won't even realize it, and you will keep reading the stale old data. So that is when you read. How about when you write? When you write, you again have the same problem that the data might be updated only in the cache. So let's say if you are trying to write to an LED array, you want to show something on the LED. And if the cache follows a write back policy, we have a problem. If it is following a write back policy, it will be updated only in the cache, and only when the particular cache block is flushed by a replacement algorithm, the actual data gets returned to the actual location. So whatever you write will not be reflected on the LEDs immediately. And if that cache block remains there without being flushed for a long time, it will take quite some time before your result appears on the device, or result is pushed to the device. And that's problematic, right? So that's why in memory mapped input output, before you do any read from an input output device, you invalidate the cache. Basically, you typically don't invalidate the whole cache, but you tell the cache controller, the address range from this range to this range should be invalidated. This has to be done explicitly, so that the cache controller will mark all those blocks which are within this address range as invalid, so that a read from that location will be treated as a cache miss, which will force a read from the actual location. How about when you write? We had the problem that any write will be first reflected only in the cache, and reflection to input output device can take a long time, right? Until the block is replaced by a replacement algorithm. So this can be forced by doing a flush. So you can tell the cache controller, oh, this address range should be flushed. Flushing the address range means forcing any block within that address range to be returned back to the memory. And in this case, return to the input output device. So before I read, you have to invalidate the cache. After I write, you have to flush the cache. This has to be done at a software level. And this complexity wasn't there at all here, because cache is connected only to the memory bus, not to the input output bus. Now, last problem is volatile keyword is necessary but may not be sufficient. How many of you know precisely how the volatile keyword works? Heard of this keyword called volatile? Whenever you do input output, you typically use the term or specific the keyword volatile. So if let's say you are trying to write to a location in the input output device, okay, typically we will use unsigned int for that. For reading and writing registers, the typical data type used is unsigned int, because when you declare something as unsigned int, the compiler generally does not do funny stuff like sign extensions, etc., which are meaningless when it comes to input output. So you will typically use unsigned int star. Okay, so you will have something like unsigned int star some register, some peripheral register. Okay, so if this is, let's say, a register which has an address PTR, so you would have something like PTR is equal to the address of the device, ABCD1234, for example. And then in order to write to this device, you will do something like, say, star PTR is equal to something, right? But if this address corresponds to an input output device, you will typically need to add volatile. Now, volatile is a keyword which forces the compiler not to make any assumptions regarding what is the value in that location. So, for example, let's say if you write a code like this, so A is equal to B, okay, and then C is equal to A. If you write a code like this, what will happen in an optimizing compiler? An optimizing compiler, oh sorry, not C is equal to, yeah, correct. An optimizing compiler will optimize this to something like C is equal to B. There may not even be a variable A in the compiled code, because the compiler will realize that, hey, there is no need for A. But things or story will be different if this corresponds to an input output device, where what you wrote is not necessarily what you read. So sometimes when you write, you will be writing the data to be sent out. When you read, you will be reading the data that was received. Okay, and unless you have a loop back connection or something, what you wrote is not necessarily what you read, or what you send is not exactly what you receive. In which case, this optimization doesn't really work. You see, if the compiler does this optimization, you are getting it seriously wrong. Because here you are actually sending, it was an output operation, here it is actually an input operation. It just happens to have the same address. And it's not uncommon at all that you have some register where when you write, that will be sent out. When you read, the value that is received is read, which is not necessarily the same value. And then you should tell the compiler, hey, I know what I'm doing. Okay, don't try to think that I am stupid and I wrote this code because I didn't know how to optimize code. Okay, here what is intended is to follow exactly what you wrote rather than trying to do any kind of optimization. So when it appears on the left hand side, write it. And when it appears on the right hand side, read it. Right? And that reading writing process should not be short circuited. It should not be bypassed. It should actually be written here and read here. And that can be done by declaring A as a volatile variable or a volatile pointer. If it is a pointer, then it would be something like, say, star A, right? Or asterisk A. And in this case, you will declare the type of A as something like, say, volatile, unsigned, in star A. So this will be the declaration. So that volatile keyword will force the compiler to write when it appears on the left hand side and read when it appears on the right hand side, rather than making any assumptions regarding what its value could be. So that is the significance of volatile keyword. But why may it not be sufficient? Like, assume that a writing would mean it's a real write and a reading would mean it's a real read. Now we have ensured that it will not be short circuited to this by using volatile. Now is that okay? Well, it looks okay provided the order will not be rearranged by the processor. And in this case, the processor will not rearrange the order because it can see that the addresses referred to is the same. So rearranging wouldn't really work. Okay? But story would be a bit more complicated if this was something like, say, D. Then you might think rearranging is okay. Rearranging is indeed okay if D and A do not refer to the same memory address, provided they are normal memory. But for input output, that may not really be applicable. Okay? For example, you could have a hardware where D is the register that you write to send the data. And in response to the data that you send, another hardware here will put in some value into A in response to the data that you sent. And this is the data that you read. Now, if the order is rearranged, the functionality is messed up. You see the problem? You are supposed to put some data into D that will be forwarded by the hardware to some external device, and that external device, based on whatever it got, will send back something, and that is to be read from A. So A is in some sense a response to what you put to D, or what you read from A is a response to what you put into D. So if the order is rearranged, the functionality is messed up. So you have to tell the hardware, do not rearrange these instructions, even though they actually do not refer to the same memory location. These are two separate registers, but it's not like they are completely independent. There is some dependency which the software can't really see. It's a very indirect dependency which could be very application specific too. Like, it depends on the nature of the device here, which the software programmer should know, and if the programmer doesn't know, it may not work the way it is expected. So you have to tell the hardware, do not rearrange these two if it's a case like this. How can you do that? You need to insert a memory barrier instruction between the two, okay, which are called memory barrier instructions or fence instructions. So you need to execute an instruction called a fence instruction, and there won't be any rearrangement of memory addresses or accesses about that fence. So all accesses before the fence will be done before the fence, and all the access after the fence will be after the fence. So you are putting a barrier there, memory barrier. So that's called fence instructions. You can read up more if you are interested, even though I believe I did explain the complete idea. Okay, so that is the problem with memory mapped input output. So you see, it does bring in quite a bit of issues, even though it looks pretty simple. And this scenario that I mentioned, writing to one register, causing it to be sent, and the response read from another register, is a simple illustration of the idea. It could actually happen even without sending or receiving any data. Okay, again, those who have taken EE2028 might know there are registers like bit set reset register, bit reset register for GPIO in the system on chip that we had used. And they are indirect means to access or manipulate a certain hidden register, which is the output register. So you could have scenarios where you write one value to a register and that indirectly changes another register. So what you read back is not necessarily what you wrote. So there could be interactions between all these so-called registers in a way that is not typically anticipated by the programmer. You cannot treat these registers as having a behavior that is very similar to memory. Memory behavior is such that whatever you wrote is exactly what you read, which is not the case with hardware registers or peripheral registers. Okay, so in all those cases, a typical software mindset can get you into serious trouble. Now, in our lab, in the lab that you are doing, that is a processor that you are, or system you are designing, we are actually using MMIO. We had specific address ranges for memory and peripherals, right? So there was a certain range for instruction memory, certain range for data memory constant, which is non-volatile, data memory variable, which is volatile. Then we had certain addresses for LED, push button, other peripherals, etc. Right? So altogether, what we have is a memory map. So every processor will have a memory map which specifies what are the address range for each type of peripheral. And the memory map that you have used in the lab is something which I created. Okay, based on just mostly based on random choice, not so much thought or systematic approach was or has gone into that design. Okay, there is some logic, some reasoning, but mostly random. So this is a mechanism that we used in our lab, and if you go through wrapper.v or vhd file, you can actually see the address decoding and the entire memory map. If you haven't done so, please do so. Okay, if you go to the wrapper file, you can see some part where we look at the various address ranges and activate the specific devices corresponding to that. So the overall picture looks kind of like this. So you have your processor. The processor issues the address. Address is unidirectional from processor to other devices. The address goes to an address decoder, and the address decoder activates the specific device. So for example, if it is memory, then memory is activated. If it is an input-output device, okay, give me a moment. Okay, so this is for write activation. So if you are trying to write to a certain location in the memory write enable will be asserted if it falls within the address range of memory. So for example, if memory is within the address range 002, let's say FF, then sending an address between this range, and if it is a write operation, will cause memory to be memory write enable to be activated, and then the exact location will be from the address. Typically, only some lower order bits of the address is enough to specify which location in the memory it is, not the full address. Okay, it depends on the capacity of the memory. And the data to be written is the write data from the processor. Okay. And similarly, if it is for this input-output device, there is again an enable here, and the data is here. So when enable is activated, the data gets latched into the register that feeds the input-output device. Like for example, your LED. Okay, you can see the implementation in wrapper.v or vhd that LED essentially has a register that feeds it, and that register is written only when the address corresponding to LED is sent by the processor. That's it. How about read? Reading typically doesn't require an activation per se. So the output of memory or these devices are all available, but depending on which device is being addressed by the processor, a multiplexer will select the corresponding data. So for example, if the address sent is corresponding to, let's say, the push button here, then the current reading from the push button becomes your read data. So this is roughly how memory mapped input output works. In port mapped input output, you will have a totally separate connection to input output and memory. So memory and input output will not be connected to the same set of wires. It's a totally separate set of wires. So for example, you could have address coming out and data coming in and out, and the data going in will be multiplexed, and one of them will come from the so-called input output, the other one will come from memory. Memory is not here, it's separate. And the connection between memory or input output is based on whether it is memory or input output, which is available as a separate pin from the processor. So the processor will activate the memory pin, or let's say if it is a single bit, it could be something like mem bar IO bar, which means if this bit is 1, the data will be from memory. If this bit is 0, the data will be taken from input output. So there is one bit, one external pin, which will allow the processor to differentiate between memory and input output. There is a separate selection involved. So if the instruction is an in or out instruction, then this bit will be 0, so that it is input output that is taken in. Otherwise it's memory, so something of this sort. Now, next question to be answered is, how exactly does the data transfer take place? So if you are talking to a memory or input output device, how do you really transfer the data? There are two approaches, PIO, not to be confused with PMIO, PIO and DMA, programmed input output or direct memory access. In PIO, the processor reads the peripheral register and places the data into a location in the memory. So let's say you have memory here, input output here. So in order to read an input output device, the processor will issue the address corresponding to IO device, read it, and then place the data somewhere in memory for further processing. So it is done using a combination of LDR, SDR type instructions. LDR to read, SDR to write. And typically the data from an input output device is big enough that it cannot be contained in processor register, so you will have to write it to memory. Okay? It could be something like an array or something in memory. But you have to read input output and write to memory. And the access itself, like for example, the process itself can be initiated through polling or interrupt. So there could be a register within the input output device which has a status, a new data is available. So the processor could read this bit. Once it is set to 1, it will initiate the data transfer by reading and then writing to memory. But it could also be done through an interrupt, where the input output device can raise an interrupt to the processor, and the interrupt service routine is the one which reads the data and puts it into memory. So the trigger can be polling or interrupt. But the problem with this is processor time is wasted for bulk data transfers. Especially if the input output device in question is something which is a high speed, high volume or high data device. Like for example, an internet controller. The amount of data that will come in could be quite huge within a second. And if it is read using LDR and put into memory using SDR, you will need a lot of LDR, SDR in a loop to transfer all the data. But that would be a waste of processor's time. The processor is like somebody who is to be given a very high salary. You wouldn't ask that person to do something very repetitive or routine, right? You will typically hire an intern or a low-cost resource to do that job. And that's exactly how it is in computer systems. And that low-cost resource which will do this transfer is DMA. So a separate controller is present on the bus, capable of generating addresses, bus signals, etc. and to transfer the data. So the processor, instead of doing the data transfer itself, will get the assistance from a DMA controller. So the processor will tell the DMA controller, oh, I want certain amount of data to be transferred from a certain location A to a certain location B. And then the DMA controller will generate addresses and will perform the reading and writing. And in the meantime, the processor can do something more value added, like crunching data or crunching numbers. So the CPU's job is limited to initiating the data transfer rather than doing the transfer itself. So the CPU, which is typically the OS, provides the DMA controller the source address, the destination address, and the number of bytes or words to be transferred. So the CPU will tell the DMA controller all this information. Source address, destination address, the number of bytes to be transferred, and then it may set some control bits to initiate the actual transfer. The DMA controller generates addresses sequentially and performs the data transfer. Okay, it's usually sequentially, but it doesn't have to be. Some DMA controllers do allow something called a scatter-gather mode, where it may not always be sequential. Yeah. In the meantime, CPU can perform computations which do not need the bus access, because the bus is now used by the DMA controller to read and write, right? So the DMA controller will read from the peripheral and write to RAM, or the other way around. So CPU will do computations based on the data that is in registers or cache. And the DMA controller informs CPU once the transfer is over by raising an interrupt. So the DMA controller will typically raise an interrupt to the CPU to tell the CPU, okay, I have done the requested transfer. Now the data is available in the RAM, you can do whatever you want with it. Okay? It may also be done by coding, though it's less likely. The DMA controller again will have some status registers that you can explicitly read to see whether the transfer is done or not. Okay, so that's the idea of DMA. There is a bit more to that story, like sometimes the CPU might be able to grab the control of the bus back from DMA controller if it needs some data from memory. And once it is done, the control will be handled back to the DMA controller. So all these possibilities do exist. Now, let us look at the various types of protocols or communication mechanisms. Parallel versus serial. The various buses. Some buses are parallel buses, some buses are serial buses. Parallel buses or protocols use a number of wires to transmit data bits in parallel. So for example, for a 32-bit data transfer, the 32 bits could be available on 32 different wires, and all the bits are available at the same time. Then it's called parallel. Whereas in serial protocols, the data could be sent over a single wire one by one after the other. You know about TV serials, right? Where it comes episode after episode. Okay, it comes one by one. So only one bit at a time, but over a period of time, you manage to transfer all the bits. So that's called serial. Now, which one is better? Yeah, correct answer. It depends. If one was categorically better than the other, we wouldn't be talking about the other one at all, right? The advantage of parallel protocols is kind of obvious. You can send a lot of information at the same time in one shot. Whereas in serial, you have to do it over a period of time, over multiple clock cycles, etc. It has to be over multiple cycles because only one bit can be sent in one cycle over one wire, right? So it will require multiple clock cycles, so it will require a period of time before the complete data is sent out. So that's the obvious part about the advantage of parallel versus serial. The advantage of parallel over serial. And that's why for very high speed buses, very high speed, very short distance buses, we indeed use parallel protocols or parallel buses. So all the buses that I was talking about, right, AHB, etc., they are all parallel. They are used for very high speed transfer, typically within the same chip or within two chips which are very physically close to each other. Whereas serial is typically used for anything which involves transmission over more than a few millimeters or centimeters. Whereas in the past, even parallel protocols were used for longer distances, but typically not more than a few tens of centimeters. So if you open up a PC from about 2005 or earlier, if you have one lying around, you can see a lot of ribbon cables between various peripherals. So you will have a few ribbon cables plugged onto the motherboard, which goes to hard drive, CD drive, floppy drive, etc., etc. Whereas if you open a newer PC, you won't see that many thick cables, because they have been mostly replaced by serial cables, which do not require that many number of wires. Now, why this change or shift? There is one obvious reason. Less number of wires means lower cost of connectors, etc., right? Other than that, is there any advantage that serial has over parallel? When you send information in parallel over multiple wires, on the receiving side, it may not all arrive at the exact same time. Due to various effects such as differences in inductance, capacitance, difference in fundamental frequencies of the various bits, etc., the receiver might not receive it all the bits at the same time. And this problem is called skew. A time variation in two different signals arriving at the receiving side is called as skew. Different signals travel at different speeds. So how do you ensure that all the bits corresponding to a byte or a word will arrive together or will be available for you to read for a good part of the clock cycle or clock period? So here you see the data that was sent, like 110, is now valid only for a very small window of time. So if you are not sampling within that very narrow window, the result or the data that you are reading at the receiver could be incorrect. It could be some bits from one particular byte or word, some other bits from another byte or word. So you end up with a mix of data which is very, very disastrous, right? You don't want your $1 million to go to a $0 because one bit arrived late. So how do you ensure that your data is correct for most of the time? By making sure that one bit period is very long enough that there is a high probability that you will sample all the bits from the same byte when you sample it. But then we have a problem. What is the problem? Your bit period is very long, which means the number of bits you can transmit per second, the amount of information you can transmit in a given time is low. And remind me again, what was the advantage of parallel protocols? You can supposedly transmit a lot of data in a given time. But now if your bit width has to be longer, you just negated the advantage you had. Another problem is crosstalk, where data from different buses or different wires can affect each other. So for example, if this is a 1, this is a 1, this is a 0, the voltage on this wire will become more than 0. The voltage on this wire could become less than 1. Or let's say if this is 0 volt and this is 3.3 volt, this voltage will become less than 3.3. This voltage will become more than 0, which is not good news. In a really bad case, one bit could be corrupted by a nearby bit, which is of opposite polarity. So this is called crosstalk. And these problems exist mainly when signals are transmitted over long distances. The longer the two endpoints are, the higher the chance of bits arriving at different times, the higher the chance of they affecting each other. Because all these generally manifest because of capacitances, inductances and resistances, which all increase when you are running two wires closer to each other for longer distances. So parallel protocols are good to use when distance is very short, typically micrometer or millimeter or even lower centimeter level. Anything beyond, these problems become severe enough that parallel protocols will do more harm than good. And then you go for serial, where many of these problems don't exist because all the bits corresponding to the byte come through the same wire. So there is no question of different bits arriving on different wires at different times, because it's the same wire. Yeah? Now, okay, I still have, okay, I thought I will finish it today, but I still have 5-6 slides. Maybe it's a good time to stop and we will do those 5-6 slides in the next class. And in the next class, we will also attempt to do some sample problems. Okay, I will upload some sample problems. You can look through it before you come for the class, and then I will go through it in detail in the class. Written solutions will not be provided for the sample questions. The reason is because each sample question will be having a lot of different possibilities and a lot of different concepts and deviations that I will explain in the class. If I just give a solution, it will be a solution only to the question that appears on the sample problem or sample sheet. Okay, whereas in reality I will be talking about a lot of different possibilities, deviations, etc. And all that will be lost if I give a written solution when people will just read those written solutions instead of listening to all the possibilities that I mentioned in the class. Okay, so see you all next week. So we are almost done with the lecture, just 6 more slides, and that's all from a theory perspective.